Hello, Eric. Are you alright? Yeah. So let's review the binary tree first. Okay, the binary tree. What's the binary tree has the two kids. Yeah, two kids. Each node can have at most two kids and only one root. Root has no parents, and each other node has only one parent. Okay, got it? Okay, so if a node, if this is a binary tree and every level is fulfilled, we call it perfect. Yeah, perfect binary tree. Yeah, okay. If a binary tree is fulfilled every level, except possibly the lowest one, but the lowest one can only be fulfilled from left to the right, then we call it complete binary tree. Okay, complete binary tree. So, but is this a complete binary tree?
No.
Why is that?
Because there's a gap between.
Yeah, the last level needs to be fulfilled from left to the right. And is this binary? How can we let's say? Is this a complete binary tree or fulfill perfect binary tree? No. Yes or no? No, right? Because every level needs to fulfill, but the last level needs to be fulfilled from left to right. Okay, we got it. Okay, so what's the binary search tree?
It's just like a normal thing.
And what's special about it? The binary search tree?
And the parent, no, the kid, the parent, the right.
The right needs to be bigger than the parents, and the left needs to be smaller than the parents. Yeah. So when we locate the value, try to search a value in the binary search tree, we can compare the current value. If we like, we want to find the 5. It's smaller than the root, so we know it's somewhere in the left tree, right? And we keep walking. Every time, if this binary search tree is balanced, it's balanced. The height difference between any two nodes is smaller than 1, smaller or equal to 1. Now, every time we do this comparison, we can drop half of it, right? So, what's the time complexity of locating log n way down? Because every time we drop half, okay, that's way down. Okay, so now we talk about heap. Remember the heap. Heap is a binary data structure, balance, or we call it balance. And we have two kinds of heaps: max heap and min heap. Okay, the max heap. So 100, 10, 20, 5, 6. That's okay. And then that we call it 7, 8. Okay. So what's special about max? So the root, the parent, is bigger than the kid. Okay, then we call it max heap. And what's min heap?
The opposite.
The opposite is smaller, right? 1, 2, 3, and then it'll be 4, 5, 6, 7. Okay. So the parent is always smaller than the kid. So what's special about the max heap? The time complexity to retrieve the max or min, the root, is 01. Okay? It's 01. Okay. So we want to build a heap. Why we want to use the heap? Because we want to take advantage of these, the constant time to retrieve the data from the root, which could be max or min, and to maintain it. For example, if we want to put the value inside it, if we want to insert the value inside the heap, or taking a value outside of heap, or deleting the data element out from the heap, what's the time complexity? Can you think about it? Worst case, can you guess? Make a guess. If we put like a 200 here, how can we do it? If we take 1 out of it, what can the time complexity?
For max or min?
It doesn't matter for the max. If we want to put a 200 here, so you can imagine there will be a restructure of this, right? Yeah. So could be if we're comparing. We sometimes we need to swap the parents with the kid and swapping out of the until we reach the root, right? So the time complexity will be O log n, right? Yeah. To delete it as well, if we delete some, the best case is what? If we just delete this one, this is the leaf, then we just delete it, that will be O1, right? But if we want to delete the root, Then if we want to delete the root, we need to do some rearrangement, right? Yeah. Sometimes involving the swapping the parents with the kids, so the time complexity will be over log n as well. Okay, but these are quite complex algorithm, right? So which we will not cover today, but you need to get this general idea of this to maintain a heap. Usually takes O log n to add a new element in or to remove the element. Yeah? For example, if I want to add another element like max heap like 1, and I can just put it here, right? Without restructuring the main heap, right? Look, we just put it there. The complexity will be just O1, right? Yeah. Okay. So that's the why we're using the heap. Okay. So how can we store the heap in an array? For example, like this: 0, 1, 2, 3, 4, 5, 6. How can we store this in an array?
0, 1, 2, 3, 4, 5, 6. Oh yeah.
Yeah, we can just put it because look, it's a complete or it's a complete. Yeah, complete binary tree.
So we can do anything.
Complete. Perfect binary tree. Yeah, remember, perfect is kind of complete, right? Perfect is kind of complete. This is a perfect. And if we remove some of the elements from the lowest level, the leaves from the right, then it could be complete. So if it's complete, we can just put these, look at it one by one, level by level, yeah? Buffer search, yeah? Usually like buffer search, 0, 1, 2, 3, 4, 5, 6. Okay, so look for this index, yeah? This index. If we want to retrieve the left kids, what's the index of the left kid? If the parent is I, what's its left kid index? What's its left kid? What's its right kid? If this is I, what's the index of this?
It's +1.
+1 times 2 +1, right?
Times 2 +1.
And what's this? Times 2 +1. What's this?
Times 2 + 2.
Yeah, times 2 + 2. Okay. Got it? For example, 2 times 2. Why? Look, 2 times 2 + 1 is 5. Why you said +1? +1 is here. Got it? 2 times 2 + 1. 2 times 2 + 2. Got it? Okay?
Yeah.
Okay, so given a heap, max heap, let's say today's task, given a heap, we want to verify if it's a max heap, okay? Because for the max heap, is that each node is always bigger than kids, right? Yeah, and we're using the index, okay? So how can we do this? How can we do this? Define is max heap, and we give him the numbers, okay? Numbers. First of all, we want to find out how many of them, right? What's the function to find out how many numbers in the array, in the list? Length. Okay, then how we want to go to the for I the index, yeah, in range what? Range what? If we want to check if do we need to go through the whole, or we can just go through half?
Because we half then.
Yeah, because we don't need to go through we can only go through the half, because if it doesn't have any kids, the leaves doesn't have any kids, we don't need to check, right? Yeah, so go to half, n divided by 2. Okay, then what? If what? If what? If nums I, if it's smaller, right? Because it's a massive. If it's smaller than nums, what's the left child of the nums I? What I? What's the left kid of I?
Times 2.
Times 2 and what? Times 2 plus 1. And then if this, we return what?
Times 2.
Return what?
Oh,
True or false? True or false? If it's the opposite, We want to check false, yes, because for each nums I, it needs to be bigger than nums I plus 2 plus times 2 plus 1. And we also need to check if I smaller than what's the right kid? I what? What's the right kid? What?
Times 2 plus 2.
Yeah, and then return false. And then return true here. Okay, so there's a small problem is that sometimes these does not exist. Its kid does not. It's the left or right kid does not exist. So we need to check if this index is smaller than n, right? So we need to put another n here. So if what I times 2 plus 1 is smaller than n, right? Okay, and then here, if I times 2 plus 2 is smaller than n, if we have the right kid, and also the root is smaller than the kid, then we return false. Got it? Make sense? Yeah? What's the time complexity? What? What's the time complexity? What? What's the space complexity? 1, yes. Okay. Okay, so I'm going to erase this bit only. Yeah. Okay. So you can tell me if what? Come on. You want to write?
If 2.
If what?
If
Two.
And.
What?
If and.
N. What's why? If what? If what n? Come on. You can copy that. Come on. If what?
If.
Yeah.
All I see is and nums.
Okay, that's okay. So what do you want to write? If what? Come on.
If this 2.
Sorry, if they what?
I don't see where you're talking about.
I want to compare the right kid. Okay, so how? This is
And.
if n. No. There's something here. Remember, I just talked about how to check it.
2.
If what?
2.
2? Think about it. What did we talk about? Think about it.
We talked about.
What are we doing here? What are we checking here? What are we checking here?
2.
2? Sorry. What are we doing here?
We are checking the
Checking what?
right,
This is left or right?
left,
Okay, then what should we checking here?
right.
Okay, so how do we check the right? There's some if some
times 2 plus 2.
sorry, if plus 2. If I times 2 plus 2 smaller than what?
Then
We all want to check if we have the right kid has
n.
yeah, and what?
And nums I. Smaller nums I times 2 plus 2.
Yeah, come on, you can do it.
Return false.
Okay, so what's this bit? Before this, what? If what and this? If what? Come on, you do it here. So what should I do? What's this bit?
If I times 2 plus 1 smaller than n.
Yeah, and okay, got it? Well done today. Good job. Bye bye.